Hi, my name is Manish Saraya. In this video, I will be talking about online exploration of tunnel network leveraging topological CNN-based world predictions. This work was done at Collaborative Robotics and Intelligent Systems Institute. Robots are increasingly tasked to explore unknown environments. Applications of robotics exploration include subterranean mapping by the coal mine companies, search and rescue missions, and for situational awareness. In order to efficiently perform exploration tasks, the robot has to adaptively select navigational goals that result in rapid discovery and mapping of an unknown environment. Figure in the right shows a robot exploring an unknown environment. A frontier is defined as the boundary between known and unknown regions. In this scenario, the robot has to keep making decisions about which frontier to navigate in order to explore the environment efficiently. A key challenge of robotic exploration is reasoning about the unknown regions of the environment. As the robot has no information about the unknown region, frontier selection becomes difficult. Thankfully, tunnel environments exhibit interesting topological structures. The figure shows a tunnel network having loops, dead ends, and intersections as shown. Topology can provide a high-level overview of the environment. Can we use topology to improve robotic decision-making in unknown environments? This is the main question we want to answer. A short answer is yes. Topological structure can be robustly extracted by persistent homology. Homology is a method to compute cycles. Figure in the right shows two cycles, blue and red, for a three-dimensional torus shape. Persistent homology is a method to compute cycles in a noisy shape such as 3D torus shown in the figure. In this paper, we propose a topological learning algorithm for predicting unknown environments to inform decision-making for efficient exploration. Robotic exploration is one of the prominent information gathering problems found in the literature. There has been work on exploration without prediction. One such approach is closest frontier exploration, where the robot selects the frontier which is closest to it. The figure shows a robot exploring an unknown environment and selecting a frontier which is closest to the robot. However, these approaches do not reason over subsequent observations. One of the approaches in prediction-based exploration is to maintain a database of structures. The robot predicts future observation values by matching the currently explored structure shown in the left to a database of previously seen structure shown in the red box. However, these predictions are limited to local structures. We argue that using topology, which provides a high-level overview of the environment, can predict global structures of the environment. Image inpainting has been used in deep learning contexts to fill irregular holes in an image. The approach trains a neural network using a database of similar images. During test time, the network uses contextual knowledge of the known image to predict the unknown regions. We leverage this inpainting approach with topological features in the environment to predict the unknown regions. Persistent homology has been used in deep learning contexts. The image shows a segmentation task. In the left, we have the neuron image, followed by the ground truth segmentation. It can be seen that the network trained using persistent homology can reason about the small disjoints in the segmentation, leading to better performance. Now, let's describe our problem more formally. The environment is represented by a navigation graph as shown in the figure. Each vertex is either open or closed, where open implies the location specified by vertex as open free space. Closed implies a location as unreachable by the robot. Edges are connected as a four-connected grid. Edges are only connected between vertices when both the vertices are open. At time t equal to 0, a robot starts at a predefined location shown in red. The robot can navigate along connected edges. Each single edge traversal take one time step to navigate. The environment graph is initially unknown to the robot, but is revealed as it explores the environment. The robot can observe 4 adjacent vertices as open or closed. Given these environment, motion, and observation models, we aim to maximize the number of unique vertices visited at each time step. The block diagram shows our algorithm overview. While training, our network takes partially explored map as input and outputs predicted map. This predicted map is taken by the loss function module. As the loss function has access to the ground truth map, it can evaluate how good the predictions are. While testing, we again take a partially explored map as input, and the network outputs the predicted map. This predicted map is used by frontier selection policy to generate action for the robot. These predictions do not need to be perfect, point-to-point matches to the ground truth, but rather should provide a meaningful estimate of the unknown parts of the environment. Our prediction method consists of 2 loss functions, topological loss and image in-painting loss. The main idea of the topological loss function is to match the topological structure between the predicted environment and the ground truth environment. Topological loss first matches the zero-dimensional structures such as connected components. In the figure, as there is one connected component in the predicted environment and ground truth environment, there won't be any loss due to zero-dimensional structure. However, there is a mismatch between the number of one-dimensional structures, such as loops, in the ground truth and predicted environment. Hence, there will be a loss associated with one-dimensional structures. Persistent homology tracks topological features at a spectrum of intensity thresholds. A persistent homology diagram consists of birth and a death of zero-dimensional and one-dimensional structures. One of the one-dimensional features can correspond to one of the loops as shown. Similarly, other dots can correspond to other loops. The zero-dimensional structure corresponds to one of the connected component in the predicted image. One can threshold the left image and count the number of loops, but this won't provide how important a particular structure is. Persistent homology thresholds the predicted image at a spectrum of intensity thresholds and computes the birth and death threshold of each structure. The figure shows an illustrative persistent homology diagram consisted of predicted structure in red and ground truth structure in yellow. We compute correspondences between these structures using the Hungarian assignment method. The corresponding cost is the Euclidean distance between the predicted and the ground truth structures. This cost defines our topological loss function. As topological loss cannot reason for size and spatial relationship between structures, we use in-painting loss to address this issue. We borrow the in-painting function from the prior work. We use per pixel L1 loss in explored and unknown regions. Contextual loss such as style and perceptual is used to have contextual knowledge about the environment. Lastly, we use a smoothing loss to maintain continuity. Our total loss function consists of both topological and in-painting loss. Some of the weighted parameters are taken from prior work and some are manually hand-tuned. We use a unit-like architecture in this work. It is useful when input and output image are of the same size. The network compresses the input to high-dimensional feature space to obtain contextual knowledge of the environment and does upsampling with the help of skip connections to obtain predicted map. We provide information value to each frontier based on the number of unexplored vertices predicted beyond it. We also consider the cost to reach a frontier before making a selection. Intuitively, we want to select a frontier which is closer to the robot and leads to more unexplored regions. We test our approach on 4 real-world mines network as shown in the figure. We train and test our approach on procedurally generated realistic mind maps as illustrated in the right figure. We generate these maps using non-uniform Gaussian mixed models. We illustrate example exploration trajectories through the Edgar experimental mine. When performing exploration with our proposed method, reasonable prediction of the ground truth world are achieved at all time steps. Although the predictions are not a perfect pixel to pixel match, it correctly identifies the region of high values. This drives our prediction informed exploration strategy towards the high value region in the top part of the world first. On the other hand, the closest first strategy arbitrarily picks between frontiers adjacent to the current location. In this case, the robot begins exploring towards the dead end in the lower left, which results in backtracking early on and therefore poorer exploration performance. We do ablation study of our losses used in this work. We compare performance of the network trained with topological loss, without topological loss, pixel-wise loss only, and lastly with no learning closest first method. Experimental result with the 4 real-world mine environments are illustrated in this figure. In all 4 mines, our proposed approach outperformed all of the comparison methods and was competitive with the Oracle solution. In particular, at 60% exploration of Edgar mine, our topological method is 30% faster than the closest first method. And at 60% exploration of Chilean mine, our topological method is 28% faster than the closest first method. These results show that our method results in more effective exploration since it focuses on exploring the predicted high value regions first. We also test our approach on 100 procedurally generated maps. Our method took 27% fewer time steps to explore the first third of the environment compared to closest first method. 10% fewer time steps to explore the first half compared to closest first method. On average, all the methods took 172 time steps to complete full coverage. In conclusion, we presented an exploration strategy which exploits subtle structural cues in tunnel network for efficient exploration. Our simulated experiment demonstrate a significant increase in exploration rate compared to techniques that do not predict and exploit topological features. In future work, we are interested in generalizing the approach for different problems, such as non-uniform coverage objective and motion costs, or larger and 3D environments. Other learning methods for predicting would also be worth pursuing, such as extracting probabilistic inferences from the CNNs. We would also like to use dataset of real tunnel network for training our model if made available. Multi-robot generalization would also be interesting. Thanks for watching this video. If you have any questions, please email me on the listed email address. Thank you.